I'd like to thank the organizers for the chance to speak today and to share some of my thoughts on some of the challenges that are facing machine learning in drug discovery. I think some of these are some relatively unique challenges that people may not be encountering in other fields. I wanted to start out just by providing my perspective and let you see where I'm coming from. So I've been working in various aspects of artificial intelligence since the mid-1980s and working in machine learning since the early 1990s. And although I've implemented my share of machine learning algorithms, I really think of myself more as an end user of machine learning methods than I think of myself as a machine learning methods developer. So hopefully you'll take this from that perspective. When I look at applying machine learning in drug discovery or really in any other field, I think of it as having three major aspects. The first is the data. If we don't have the right data, if we don't have the right quality data, if we don't understand the error in that data, it's going to be very difficult to use that data to build a machine learning model. The second aspect that I think is vitally important is the representation. In particular, in drug discovery, how do we represent molecules in a fashion that can be processed by a machine learning algorithm? And then finally, with algorithms, how do we relate that representation back to some observable endpoint in our data? I think all three aspects here are important, but we're going to focus today mostly on the data and the representation and some of the challenges there. So let's start out by talking about data. As I mentioned, to me, this is the most important aspect of the problem. We need to have the right data. And unfortunately, the data that we typically encounter in pharmaceutical research and drug discovery is not ideal for machine learning. To start out with, the data sets that we have are often very sparse. It turns out that every molecule is not tested in every assay. You'll only run your most expensive assays on your most important compounds. So you're going to end up with this very sparse data matrix. And how do we deal with that? Another challenging aspect of the data is the fact that our assays are often run over a relatively limited range of concentrations. For instance, your molecules may not be soluble enough to assay above 30 micromolar. So what it'll end up with is that our assay data shows a large number of values as greater than 30 because that's the top concentration of the assay. Well, what does greater than 30 mean? Does it mean 31? Does it mean 300? Does it mean 3,000? We really don't know. So we need better techniques for addressing this. If we're trying to do regression, we can often be confounded by the fact that our data spans a relatively limited dynamic range. We may only have data that spans one or two, if we're lucky, 3 logs. So given experimental errors can make it very difficult to do regression reliably. In many cases, it may look like we have a lot of data. We may have 30,000 pharmacokinetic data points. But it may also turn out that those assay measurements were in 5 different species at 12 different concentrations using 8 different vehicles. And it suddenly turns out that what seemed to be a large and rich data set is in fact just a set of smaller data sets that can't be combined apples to apples. And then finally, drug discovery programs tend to work in limited areas of chemical space, and we often can't reliably tell whether a new molecule is similar enough to the molecules that we trained our model on, and we'll talk a little bit more about that later. So next up, We have a number of benchmark data sets that are now being widely used in the literature. One of the issues with these data sets, though, is that there hasn't been a lot of quality control. So you'll find large numbers of chemical structures in these standard benchmark data sets where the molecules there were actually assay artifacts. So they didn't give you a genuine response. These molecules simply interfered with your assay. So if you take any of the molecules that are on this slide and you showed them to an organic chemist, it's highly likely that they wouldn't trust any of the results for these. And yet, those molecules end up in our benchmark data sets. Another confounding factor in building these models, especially from benchmark data sets, is that a single chemical structure may not necessarily correspond to a single endpoint. And a great example of this is aqueous solubility, the amount of molecule that dissolves in water. And this has become a standard benchmark for many machine learning methods. The problem is that in cases like the one on this slide, this molecule difusenol, depending on how it was crystallized, can have a very different solubility. So you can see here on this slide, there are 4 different crystal forms of diflusenol, and the solubility of these can differ by 100-fold. So if you're making a prediction, which form are you predicting? Another aspect to this, especially when we look at benchmarking virtual screening, is that we tend to create these benchmark data sets. We'll take a number of active molecules from the literature, and then we'll look at the ability of our machine learning method to identify this molecule among a sea of decoy molecules. And these decoy molecules are put into the benchmark sets by picking other molecules that have similar physical properties, molecular weight, lipophilicity. But as you can see from this plot on the right, we've plotted the chemical space of this data set. We've plotted the active molecules in blue and the decoys in orange. And you can see that just based on this simple representation, we were able to pick out the vast majority of the actives from the decoys. So it turns out to not be a very challenging problem. Another issue that we have to deal with here is representation. So how do we, as I said before, represent a molecule in a form that can be processed by a machine learning algorithm? If we take a look at a lot of other fields, they've agreed on a standard representation. So for images, we can treat images as pixels. Those pixels can be represented by numeric values. We can take vectors of those and use those to do machine learning. If we've got text, we can transform that text into things like bag of words and process that. The unfortunate part is that we still don't have a standard means of representing a molecule in a form that can be interpreted by a machine learning algorithm. For years, we've used these molecular fingerprint approaches, which seem to work reasonably well, but still leave a lot to be desired. In these approaches, we take a molecule, we look for the presence or absence of particular substructures. We then can use that to encode either a bit vector or a real valued vector describing the molecule. We can then use those vectors as input into a machine learning program and use that to build our models. And as I said, it's a reasonable way to go, but there's still a lot of improvements that can be made. One set of techniques that seem to be making some advance in the field is using neural networks to create new molecular representations that can be related to data. And there have been a number of approaches, including work on using graph convolutions or message passing neural networks. But there are still a lot of open questions there. We don't know how much data is required to build an appropriate representation. We don't know when the representation from one set of molecules is applicable to another set. So I think there's a lot of work that needs to take place to answer some of those questions. Another thing that we have to consider is that for the most part, we've been treating molecules so far as graphs. So we're just looking at the graph representation of the molecule. We don't consider the fact that the molecule is a three-dimensional entity and that entity can be flexible. And as we start considering flexibility, we really have to think about the fact that we don't have straightforward ways of relating multiple representations of an object, say multiple conformations of a molecule, to a single biological or physical property endpoint. So I think there's still a lot of work to be done there. There's been some interesting inroads made by Rafael Gomez-Bombarelli at MIT and by Alpha Lee's group at Cambridge University, showing that they can create models based on 3D representations that seem to, at least on some data sets, be roughly equivalent to graph-based models. But it seems like we should be able to do better, and we should be able to use 3D representations to come up with models that are more transferable across chemotypes. Finally, we can talk about algorithms. I think there are all sorts of advancements coming out in the open source community from Google, Amazon, Facebook that are very useful in our field. I've been very happy to see people coming into computer-aided drug design from computer science, where it seems like publishing the source code along with your paper is the norm. I wrote a recent viewpoint in the Journal of Computer-Aided or the Journal of Chemical Information and Modeling, making that same point and really saying that our field needs to have standards for the inclusion of code with new methods. I'd like to just touch upon a few other aspects that I think are critical. So, we've talked a little bit about generative models and using models to generate new molecules. In many cases, the molecules created by these models are diverse, and that's great, but that doesn't really fit in with the standard batch workflow that we have in drug discovery. If you're coming up with 10 molecules that are all very different and require different routes to perform the chemical synthesis, this is going to be a very time-consuming process. Whereas if we could come up with sets of molecules that are similar, that could be exploited in a similar set of chemical routes, I think that this could help us to advance the field and move things in the appropriate direction. I think another key issue that we have to deal with is model applicability. So when I talk about this to a general audience, I always make the point that if I trained a model on a set of parrots, I'm not sure how much it's going to be able to tell me about the properties of a set of penguins. And we run into a similar situation with molecular modeling and in building predictive models for chemical properties. Given a new molecule like the one on the right and a set of molecules that I trained on the left, how do I know whether my model is going to be applicable to that new molecule? And the approach that we've taken to this in the past is by simply calculating the similarity of the molecule that we want to predict to the molecules in our training set. But we're still in the realm of rough heuristics there. And as I mentioned earlier, I think as we get to these more complex nonlinear representations, these notions of similarity are not straightforward. So I think this is still, we need to get a better handle on what the confidence is in our predictions for a particular new molecule. As I mentioned before, we're still in a period where there's not enough data to enable us to develop new methods. Everybody's working on data from Kemble and other public sources. And I think we need to get to a point where we have more partnerships between industry and academia that enable these models to be tested and developed in a more robust environment. Another factor that I think we have to consider is the fact that drug discovery is by its nature a multi-objective optimization process. I think we need to be able to not only optimize the binding of a molecule to a single protein, we want to make sure that it doesn't bind to lots of other proteins. We need to make sure that it has reasonable pharmacokinetics, that it has reasonable physical properties. We don't want this to be a game of whack-a-mole where we fix one property and end up having a detrimental effect on another. And I think far too often in drug discovery, we see a trajectory that looks like the blue line in the plot on the right, where you fix one property and then you have to take 2 steps back to fix another, and then you make another change, and then you lose potency. So we'd like to see something that's closer to the black line that gives us a more smooth, multi-objective trajectory to our final endpoint, which would be a drug candidate. I've been working in pharmaceutical research as a computational chemist for 25 years. And I've discovered over that time that I really only have 2 jobs. I need to be able to convince somebody to do an experiment or to convince somebody not to do an experiment. This is my job. And in order to convince somebody to do an experiment, I really need to be able to explain the reasoning behind a prediction. It's always easier if I can go back to the fundamental principles of physics and chemistry and explain specific interactions and why a molecule is predicted to have a given activity. These interpretable predictions also enable teams to move forward more quickly. So I think there's still, a lot of work to be done on model interpretability. I think another thing that we have to come to grips with, and this is coming back to what I spoke about earlier with generative models, is the idea of invention and automating invention. But how do we quantitate this? And there was a response that my colleague Mark Marco and I wrote to a paper that came out earlier this year that described the use of a generative model to come up with an inhibitor of DDR1, a target that's been implicated in fibrosis. And what we pointed out was, yes, the generative model came up with a new molecule, but that new molecule in the center was also very similar to molecules that had been published previously and even similar to a marketed drug. So how do we really quantitate this process of invention? I think this is something that we need to set some more standards for. So finally, I think in order to move the field forward and in order to progress, I like to borrow this analogy from data science from Drew Conway on his blog. So he pointed out that in order to be successful in data science, someone needs 3 things. They need to have the hacking skills, understand machine learning. They need to understand math and statistics so that they're not fooling themselves, but they need to also have substantive expertise. And I think for our field, one of the big challenges is the representation. I don't think you can develop that representation unless you have an understanding of the fundamental chemistry, physics, and biology. And then, finally, I think the other thing that's key to advancing our field is these collaborations like the one in the paper that I'm showing here between MIT and a number of pharmaceutical companies. We need to be able to demonstrate that these models work in a real world setting. So, finishing up, I think it comes back to these three factors. We need to have the right data. We need to develop better representations, and we need to take advantage of all these algorithmic advances. Thank you so much for your attention.
Thank you, Pat, for that amazing overview. And so now we have a couple of questions from the Discord. The first question is from Steve, who asks, if you had to choose between A, more data, B, better data, or C, better algorithms, which would you pick? Which directions are going to raise the ceilings for these approaches? And I think we clarified that you get to pick two rather than just one.
Well, if I have to pick two, it's going to be more data and better data. I mean, I think we need to make sure that we have high quality data that we can trust. And, you know, if we take a look at some of the common tasks that people are using in benchmarks like solubility data, there are a lot of factors that go into that, which really aren't considered in these data sets. So it'd be great, for instance, if we had solubility data sets that were composed entirely of compounds that were crystalline or entirely of compounds that were amorphous, so we could get a much better idea of what the true scope and limitations of these predictive models are. I mean, I think still largely the field is starved for data, especially when we compare what we're doing to a lot of other fields in machine learning.
Yeah, makes a lot of sense. So relatedly, if you had the power to direct all of ML research towards one challenge in one scientific challenge, which aspect would you like to see more focus on?
I think, I don't know if I can pick one, so I'm going to cheat again and pick a couple. Yeah, I think one of the real critical issues still for us in drug discovery is confidence in the models and really understanding what your applicability domain is. So I've got a set of molecules that were synthesized in one drug discovery project. Now I'm starting up a new drug discovery project. How much can I transfer what I learned from one project to the other? You know, one would hope that we're going to get to a point where we're learning the fundamental notions of chemistry, biology, and physics, and everything will be perfectly transferable. But I don't really think that that's the case right now. I think the other thing that I'd really like to see more of is explainability. As I mentioned in my talk, you know, drug discovery is a team sport. So I'm working with chemists, with biologists, with structural biologists. You know, and my job is to either convince somebody to do an experiment or convince someone not to do an experiment. That's much easier if I can relate the predictions from the models back to some fundamental principles, you know, and also the understanding of those principles and the principles behind why we're seeing molecules as active or inactive will then spark the creativity of experimentalists. It will get chemists thinking in a different way and thinking about how they can design a better molecule. You know, so far, it seems like the other thing is we don't really have benchmarks right now for interpretability. Most of the papers I read, just it's more happenstance. It's like, look, we looked at the interpretability of the descriptors and I'm looking at solubility and it says that a primary amine is important. And well, that must be right because we all know that primary amines are important for solubility. It's like, yeah, you told me something that we all already know. But, you know, so, but can we put together benchmarks where we know, where we've got sets of physical characteristics? And then, you know, can we then go and try to prospectively demonstrate that those characteristics are really important?
Let me riff on that question really quick here. What would a benchmark look like in interpretability to you? Like, what would you think would make sense for questions that might be asked or a data set that would contain interpretability? Would it be based on like real life known properties? Would it be based on like sort of dummy characteristics like where's the benzene ring in this molecule?
Yeah, well, I mean, one of the simplest characteristics, and the only place I've seen this, I think I've seen this in 2 papers now, is just using an ablation strategy where you go and start just intentionally removing features from molecules and then looking at whether your explainability metrics are then pointing out those features. So I think, we need to start out and get with artificial data sets where we know what the answer is. But then, I want to move from that to things where it gives you reasoning that's based or in chemistry and in physics.
Sure. So if I can clarify this a bit more, it might be something along the lines of a data set that's based on like maybe theoretical chemistry calculations or something like this.
Yeah.
Sounds good. Ben asks, I appreciate bringing up the issue of code sharing and open sourcing. Current researchers and students have to work on machine learning and chemistry and also have good code. What are things that you imagine institutions, organizations, and editorial boards could do to improve open source science, but also help current researchers?
Yeah, I mean, one of the things that I'd like to see, and you're already seeing this from journals like Science and Nature, where they actually have specific editorial criteria around the inclusion of code. It's really back to, I look at this in the same sense as a structural biologist. It used to be 20 years ago, structural biologists would just publish a crystal structure and they would just put a figure in to show the structure. And then people were like, hey, wait a second. No, you need to deposit the coordinates along with it. And I think we need to get to the point where if you're going to publish a method, it's just a requirement that your code is in GitHub, at least simultaneous with publication. And I think to a lot of people in computer science are like, oh yeah, that's logical. That's what we always do. But if you take a look at, the 4 journals that publish papers in cheminformatics, none of those 4 journals has any sort of criteria. What Journal of Cheminformatics does. The other 4 journals have no criteria for inclusion of code with papers.
Fair enough. Sam asks, what are your thoughts on the QM9 and Zinc datasets? Do they have the same weaknesses as those you mentioned in your talk, namely assay artifacts? Are there any shortcomings of the 3D point cloud representation aside from the greater difficulty from an algorithmic perspective? And then what do you think about metrics like QED?
Yeah. So I guess we're talking about then taking because a lot of people use QED as a metric for drug likeness for generative models.
Right.
To me, that's a very artificial method. And the medicinal chemist in me looks at plenty of molecules that don't look drug-like, that have very high QED scores. Mm-hmm. And molecules that are drug-like that don't. So, it's a metric, but to me, it's really no more meaningful than log P or polar surface area or anything else. I mean, it's a computable method, and I think we've shown that we can use generative models to produce molecules that maximize or minimize these computable metrics. But how well do they do against, a model that's predicting things like biological activity? And then, just to riff on things that I'd like to see, I'd love to see more work on optimizing toward multiple objectives because, in drug discovery, we're not trying to optimize one thing. We are trying to optimize one thing, which is how this drug will behave in a patient, which we don't know how to model. So we have a whole bunch of surrogates, but we're not even doing a great job of modeling multiple surrogates.
Right. All right. I think last question before we move on to the next talk, which is, Jim asks, are there any approaches to model interpretability that you've seen to be particularly effective in convincing scientists to run or not run an experiment? Are there graph heat maps like the one on your slide to show nodes and edges, how nodes and edges contribute to overall prediction? Are these things useful to chemists?
Yeah, I think they are. If, the problem is that in many cases, at least in my experience, these will also point out spurious features that have nothing to do with the biological activity. They just may be some artifact of the way that your machine learning model works. But yeah, I'd love to see things where you can point out a specific area in the molecule that says, this is important, leave it alone. This part over here, if you're trying to optimize bioavailability, you can change that part.
Got it. All right. Thanks so much, Pat.